So good morning and good afternoon, everyone. My name is Arman Shojayfard. I work for InterDigital, based in London, UK, and it is my pleasure to welcome you to this webinar series on Beyond Diagonal RIS, organized by Professor Bruno Klertz, the chair of the Special Interest Group of Communication Society on Beyond Diagonal RIS, and Matteo Marini. Today we have our eighth and final talk of the series. And it is a huge pleasure to introduce our speaker for today's session, Professor Mohammed El-Hajjar. He really does not need an introduction from me, but I will try anyway. Professor El-Hajjar is a professor of signal processing for wireless communications and the director of MSc programs in the School of Electronics and Computer Science in the University of Southampton, UK. So Professor El-Hajjar completed his MSc and PhD degree from University of Southampton and joined the university as an academic member of staff. He is now leading a research team working on various aspects of wireless communications, including RIS, millimeter wave, terahertz, ISAC, as well as underwater communications. He has a fantastic track record of publishing many papers and being inventor on many patents. And his research is funded by the UK's Engineering and Physical Sciences Research Council, the Royal Academy of Engineering, the UK Space Agency, and many industrial partners. So before we hand over to Professor El-Hajjar, so the duration of the talk will be around or under 50 minutes during this time. The audience will be muted, but do feel free to post your questions in the chat for the end, where we will have a Q&A where you could raise your hands and we will go through in a first come, first served basis through those questions to ask our speaker to provide answers. So with that, I'll hand over to you, Mohammed, to please take us through your presentation. Thank you.
Thanks for the introduction, Arman. Just share my screen. Can you see my screen?
Yes, we can. Thank you.
Thanks for the introduction, Arman, and thanks, Matteo and Bruno, for inviting me today. So during this webinar series, we had lots of exciting talks about Beyond Diagonal RIS, its architecture, its optimization, its applications. And today I'm going to walk through another architecture which we refer to as the non-diagonal architecture, which is simply referring to the fact that the matrix is non-diagonal. Let's start with acknowledgements. Again, thanks for the invitation. It's important to acknowledge the team in Southampton here, specifically King Chow, Ino, Michael, and Laish, who I work closely, and we work closely on this topic I'm discussing today. Part of the work I'm discussing today is funded by InterDigital, so we work closely with InterDigital team, that's including Ibrahim, Arman, and Elaine, and we also worked with Bruno. And the funders include the EPSRC, the Royal Academy of Engineering, and InterDigital, as I just said. So this is a sort of like a typical figure you see in most of the presentations on RIS, and I'm not going to repeat everything and motivate the use of RIS, but I'm just going to look at it from a different angle now. So conventionally or traditionally, the way we design communication systems or wireless communication systems is we consider different sort of conflicting factors, which include, for example, bit error ratio, the signal to noise ratio, the spectral efficiency, the latency, the complexity, the cost, energy efficiency, and so on. And these tend to be pushing in different directions. And we always try to design a system which gives us a trade-off of these. We can't have an optimal system which works, which is optimal in everything. We try to sort of have a trade-off. A simple example is, let's say we want to minimize the bit error ratio. So in order to do that, and ideally we want to achieve the capacity. So we want to have a capacity achieving system. To do that, we need a very long frame. And also we want to use channel coding. So channel coding with a long frame introduces high computation complexity for the decoding, as well as long latency. So now I'm just giving you an idea of what the conflicting parameters are. So we have the performance parameter, which we're trying to minimize, but then we have the latency and the computation complexity, which are increasing. Another typical example is we try to, say, maximize the spectral efficiency or achievable rate. So for example, we can use multiple antennas or MIMOs. So for that, we need to use multiple antennas, which increases the cost, as well as the processing computational complexity. Again, these are some other parameters which we consider in wireless system design. And all these are conflicting parameters, and we always aim to have, as I said, a trade-off of these. Before RIS, we used to look at the channel, which is the most challenging part in the optimization, as an unknown. So now the RIS introduced the channel, or introduced another parameter which we can optimize within these factors, which is the RIS. We're allowed to sort of change the electromagnetic properties of the signal, and then we're able to somehow control the channel. So now we have another degree of freedom, which we are able to utilize to design the trade-off that we discussed. So this is, again, a typical RIS system model, where the RIS here is used for reflection. So we have a base station communicating with multiple users. And we have the RIS surface here, which is reflecting the signal to the users. And we have the RIS controller, where the base station decides on the phase shift values that we need to use at the RIS so that the signal is sort of optimized. So this is the channel model equation, where traditionally we have y equal hx plus n, or hs plus n. So without the RIS, we have hd and then s plus n. And then what we try to do is we try to optimize the pre-coding at the base station and the combining at the user equipment. Now what we have is we have this extra degree of freedom here. So we have the parameter theta, which we can configure so that, again, we can try to optimize this. So what we can do here now is we can optimize the pre-coder at the base station, the combiners at the user equipment, and the theta here, which, as I said, gives us an extra degree of freedom to try to optimize something with, again, considering the trade-offs. So you can optimize the channel gain, optimize the bit error rate, spectral efficiency, and so on. So this is, again, a quick overview of what's RIS 1.0 to RIS 2.0. So conventional RIS, where an element, a signal impinging on an element, will be reflected on the same element. So we end up with theta, which is this theta here, being a diagonal matrix, which is saying signal coming on this element is reflected from this element. So it's basically mapping this channel to this channel here. So this, again, gives us another degree of freedom, and we can optimize. But the question arises is, can we sort of try to have these non-zero elements to be, sorry, these zero elements in the matrix to be non-zero? So these are the question marks here. So how can we get the matrix to be sort of full, or maybe just move these around, having the extra degree of freedom? And then why do we want to do this? How do we want to do this? And do we get any benefits from doing this? So my colleagues in this webinar series covered lots of aspects looking at the beyond diagonal group and fully connected RISs. I'm going to focus on this part here, which is what we call non-diagonal single and group connected architecture, which I'm going to look at the reflective mode, and then when we have multiple sectors, how we benefit from this. So this is the conventional RIS, or diagonal-based RIS, where, again, this is the reflected signal. So the signal input on one element is reflected from the same element. So we end up with this diagonal matrix here. And what we have is, if we have this illustration here, so this input channel and reflected from the same element. So now our degree of freedom is trying to optimize the phase shift on these elements here. So Bruno and his team and other colleagues worked on the fully and group connected RIS architectures. I'm not going to go through this in details because it has been covered in other talks, but I'll just present it quickly so that to motivate the idea of non-diagonal RIS architectures. So the idea of the fully connected is by simply starting looking at the matrix here. Can we have all the elements non-zero? In other words, can we connect all elements together here? So we end up with this sort of impedance network where input signal here can be reflected from any or all of these elements there. Okay. So you might think, well, this is too complicated or too costly in terms of hardware. So another potential simplification is having this group connected, where you say, I don't want to have everything connected to everything. So I have sort of groups connected to each other. Yeah, as in this example group. This group 1 has element 1 and 2, group 2 has elements 3 and 4, and so on. So this now gives me this block diagonal channel. Okay. So the question we asked ourselves when we looked at the fully and group connected is, if you look at this here, we have more elements, non-zero elements, compared to the conventional diagonal channel matrix, which means we need to do more optimization, and in terms of hardware, it will be more costly compared to the diagonal-based RIS. So this is the diagonal. So we thought, can we say we want the same number of non-zero elements in the channel matrix? Sorry, not the channel matrix, the phase shift matrix. But then the elements, we want them to be not on the diagonal entry. So in this example with 4 elements, we're saying if an signal is impinging on element 1, can it be reflected from element 2? And then impinging on element 2 is reflected on element 4. And then on 3 reflected from 4, and from 4 reflected on 1, and so on. Yeah. If I go back to the fully connected and group connected again, the connections here are reciprocal, which means that I have this symmetrical matrix, which is in this case as well. Yeah. In this case, I don't have symmetry because I have just one connection. Yeah. So we look at in a minute at how we configure these connections, but assuming I have these connections, so I just have with one element per row per column, I don't have symmetry and it's non-reciprocal. And I have the number of non-zero elements here is equal to the number of non-zero elements in the conventional diagonal-based phase shift matrix. Okay. Another example is having 6 elements. So same thing, this is for the conventional, we have the diagonal. In this example here, a signal impinging on element 1 is reflected from element 3. So impinging on element 1 reflected on element 3. Impinging on element 2 is reflected from element 4. So sorry, this is input 1, output 3, input 2, output 4, input 3, output 1, so input 3, output 1, and so on. Yeah, so this is how we're sort of defining this channel matrix. So again, not channel matrix, phase shift matrix. So our degree of freedom here, an extra degree of freedom of the non-diagonal compared to the diagonal one, is that now we need to configure these connections here. So in this example mapping, we're mapping 1 to 2, 2 to 4, 3 to 3, and 4 to 1. Yeah. So this is what I'm saying. So we have another degree of freedom here. What's the best routing between the input elements and the reflecting elements? And then we do the sort of phase shift configuration, as opposed to having just phase shift configuration and the conventional diagonal-based RIS structures. But again, I'll come in a minute of how we configure this, but just a quick figure showing the channel gain distribution for different K Ricin factors for this one conventional RIS architecture, and this one is the non-diagonal RIS architecture. So this is the normalized RIS, normalized channel gain. So we normalize it basically by the maximum possible channel gain. So that's why the maximum value in this case is 1. So as you can see here, as we move to more non-line of sight dominant channels, the conventional one, the channel gain is significantly reduced, while the non-diagonal one is more robust. We have more uniform distribution of the channel for different K values. This is the K for the base station RIS channel, and this is the K for the RIS user equipment channel. So the question is now, how do we do this mapping and how do we optimize the theta matrix? So again, this is our equation for a single user size scenario. So now we're considering base station has 1 antenna, 1 user with 1 antenna as well, and we have RIS with n reflecting elements. So this is the equation. So what we're trying to do is, what's the best or what's the optimal theta? One objective function or one possible objective function is to maximize the achievable rate, which is then equivalent to maximizing the channel gain. In a conventional RIS, where we're looking at the diagonal elements, the optimal theta corresponds to the equal gain combining, which we can write it this way, which is basically coherently matching the phase of the input channel and the reflected channel. So now this theta, we can sort of expand it this way, which is now e to the j theta I prime I. In other words, I prime is the reflected element or reflecting element, and I is the index of the impinging element. So now we have this extra degree of freedom, which is not just find theta. How do you find this I prime I matching? Then after we find this I prime I matching, then we can basically again use the equal gain combining. The question now is how to find this mapping. What we do is we use the maximum ratio combining, which is illustrated in this example here. So what we do is we look at the channel amplitude, or we can rank the channels of the base station RIS channels, rank them in ascending or descending order, and rank the channels from the RIS to the user equipment, again in ascending or descending order. So in this example here, this is the channel between the base station and the, so G is the channel between the base station and the RIS, and H is the channel between the RIS and user equipment. So what we do is we map the highest channel amplitude with the highest channel amplitude, second highest channel amplitude with the second channel amplitude, third highest channel with the third, and so on. So the mapping becomes what we have here. The highest is 1 is mapped to 2. So we have this mapping 1 to 2. And then we map 4 to 2. So we map 4 to, sorry, 4 to, sorry, 1, yeah, because this is maximum, this is second maximum. So 4 to 1, 4 to 1. And we map the 3 to 3 in this case, 3 to 3. And then we map 2 to 4, which is 2 to 4 here. So basically what we do, as I said, maximum ratio combining, where we rank the channels in the ascending or descending order, and then we just map highest to highest, second to second, and so on. Yeah. So this is the combining or mapping that we do. And then once you've got this mapping, you can do this coherent combination here. So what we do is we define theta, JR and JT, and the theta here. So JR and JT are basically allowing me to do this mapping of the input and output elements. And theta here, I can think of it as a diagonal matrix. Then these are basically combining the input with the output reflected element. So that works for a single user SISO case. If you want to expand this to multi-user MIMO scenario, where we have a base station with M antennas, and then multiple users with 1 or more antennas, and we have RIS with N reflecting elements. So again, our objective function here is to maximize the sum rate. Okay. So this we cannot simply use the maximum ratio combining in this case because the problem is much more complicated. So again, this is a optimization problem which we can use with optimization techniques. What we did is we looked at, so what we want to do now is we want to find W, which is the base station precoder. We want to find theta hat, which includes the mapping between the input signals, the impinging elements mapping to the reflecting elements, as well as the phase shift values for the reflection. So we have these three parameters we want to find. So what we can do, or what we did, is we sort of designed it. Instead of doing this jointly, we separated it into two parts. We looked at this now. So if we try to maximize this channel gain, and then we find the J and theta by doing this. And then we looked at this as the equivalent channel, and then we find W based on the equivalent channel. And this way is, I'm not saying it's the optimal way, but it is one potential solution to solve this problem. So now let's look at some results. So here I'm looking at the complexity of the different architectures versus the number of elements. So complexity here is in terms of the number of configurable impedances. So number of impedances we need to use. So clearly the conventional one is the smallest and the fully connected is the highest. And then the group connected, depending on the number of groups, will be somewhere in between. Again, which shows the trade-off of the design, complexity versus performance. So the number of impedances, configurable impedances needed in the non-diagonal one is equivalent to the number of the impedances needed in the conventional scenario. Why? Again, because the number of non-zero elements is the same. You might argue here that it depends on what architecture here, which is true. So we're not showing the whole picture here. We're just showing the number of impedances. We propose a potential implementation idea which uses some switches, which then you need to add the complexity of the switches or the course of the switches in this figure here. Another measure of complexity we looked at is the RIS or base station RIS control link load. So what information you're sending between the base station and the RIS and how much you're sending this information versus, again, the number of RIS elements. Again, same thing, conventional has the lowest, fully connected has the highest, and the group connected is somewhere in between. The non-diagonal fits here, and the reason is because in addition to the phase shift values that we send compared to the conventional, we're also sending the mapping of the input to output elements. So as you increase number of elements, the mapping information increases, and then you need to send more information. But it's still lower than the fully connected. So here we're showing the rate of the single user SISO scenario versus the distance. This is, we're looking at the RIS user equipment distance. As expected, as you increase the number of RIS elements, the achievable rate increases. And as you increase the distance, the achievable rate reduces because this increases the path loss. So here we're plotting the achievable rate versus N for, again, increasing or changing the path loss exponent value, which is as expected. As N increases, you get higher achievable rate. And then as you increase the path loss exponent, the path loss increases, and then your achievable rate reduces. So there's no surprises here. But the point here we're making is that the non-conventional or non-diagonal has a higher achievable rate compared to the conventional diagonal-based structures. And this is shown in this figure and in this figure. So this is the result for the multi-user MIMO scenario, again, comparing the conventional with the non-diagonal one, and we achieve a higher capacity for the non-diagonal compared to the conventional. In this scenario, we're using a non-line of sight dominant channel where the rising K factor was -10 dBs. So here we're showing the performance as we change the K factor. So as you can see, as the K factor increases and the channel becomes more line of sight dominant, the gap here reduces. So now this again puts the point of it's a trade-off. Where do you want to deploy this? How you want to deploy it? And what gains you get. Right. After looking at the non-diagonal single connected structures and looking at the group connected architectures, we thought of, again, How about we look at this channel matrix and have groups where we have more than one non-zero element in this rows and columns, which is an extension of the group connected architecture. So this is the single connected where you have the diagonal matrix. This is the group connected where you have a diagonal or block diagonal channel and then block diagonal matrix. And then the groups are defined based on the sort of the natural index of the antenna element. So 1 and 2 form a group, 3 and 4 form a group, and so on. So the question was, can this be extended to having sort of non-diagonal and non-block diagonal matrix? And how would you optimize the mapping between the elements, which is taking the idea of the non-diagonal single connection further. So in this specific example here, 2 and 4 are mapped to 4 and 6, 1 and 4 are mapped to 5 and 2, and so on. Yeah. So what we have here is, if we look at 1 is mapped to 5 and 6. 1 is mapped to 5 and 6. 5 and 2. So 1 is mapped to 2 and 5. And then we have 2 is mapped to 4 and 6. 2 is mapped to 4 and 6, and so on. Okay. We'll look again in a minute of how we do this mapping. But assuming we have this mapping, so again, the question becomes, how do you design your JR and JC, which is the mapping between the elements, and then find the phase shift matrix? So we define this J tilde as a diagonal block diagonal, and then this JR and JC is basically spreading the matrices, the values around depending on the mapping of the groups here. So for the beamforming design, again, the question is to find JR and JC, which is the mapping, and then find the configuration of the impedances, which gives us the phase shift values. In a single base station antenna, single user case, again, we can use the maximum ratio criterion where we can rank the channels, and then we say we group them in groups. So we take the highest group, the highest group, and so on. So in other words, let's assume we have 4 elements, and we want to have 2 groups. So 2 elements per group. So what we say is we map the highest channel on the impinging or base station RIS channel to the highest channel in the RIS user equipment, second highest, and so on. So we map the first top 2 highest into one group, second 2 highest into another group, and so on. Yeah, so this is the maximum ratio criterion. And then you can define your theta based on some optimization or using the coherent mapping. For multiple base station antennas, again, you end up with an optimization problem, which you can solve using some optimization techniques. So here we have some results comparing the fully connected, single connected, group connected, and the non-diagonal group connected architecture. Again, here, this is the number of required reconfigurable impedances versus the n number of RIS elements. Again, clearly the fully connected has the highest number of impedances. The group connected and the non-diagonal group connected have identical numbers because basically what we need, we have the same connections and you have the extra switches needed for the non-diagonal one. If we look at the channel gain, which here we're normalizing it by the channel gain of the conventional one. So this is why the conventional one has a value of 1, so normalized 1. And as we increase the number of elements, we see that the fully connected is the highest. And then we have these are the group connected with varying number of groups. Yeah. The non-diagonal group connected, as you can see here, as the number of elements increases, approaches the fully connected architecture, which gives an advantage in terms of performance. So here we are again looking at the channel gain versus number of base station antennas in multi-user MIMO scenario for increasing the number of RIS elements. And what you can see here is that the performance of the non-diagonal group connected is close to the fully connected architecture. A further extension of this work is the multi-sector non-diagonal RIS model. So the motivation of this is that if you think about the RIS in the reflective mode, that you just cover one side of the RIS. And another challenge is if you start looking at the path loss, because the path loss, based on some studies, also depends on the angle of arrival, angle of reflection from the RIS. And the best is basically when the angle is smaller, or the lowest path loss is when the angle is smallest. So if we look at covering basically two sides, we can use the star RIS, simultaneous transmitting and receiving RIS. But again, that has the challenge of the path loss because you don't have control on the angles. So this is where the idea of multi-section or multi-sector RIS can be motivated. So here, if you have basically the conventional no connection between these elements, then this is useless. Why? Because this basically is just covering this area. This is covering this area. But then with the idea or the introduction of the beyond diagonal RIS, this can be motivated. Why? Because these elements can be connected to any of these elements there. So signal coming here can be reflected from here, and then you have coverage in this area, And then the question now is, how many sectors do I have? So I'm going to ask a few questions which I don't have an answer for them, but they are still open questions. How many sectors do I have? And here we need to consider the path loss. And then another question is, if this is the input signal here, do I consider only the elements on this sector to reflect from somewhere? Or do I consider elements in different sectors depending on the angle between the transmitter and these sectors? And similarly for the user, do I just consider this surface to reflect the signal to the user, or I consider multiple surfaces to reflect the signal? Another question is, do I have the elements connected in this dimension or elements in this direction, or I get them all connected together? So this is again becomes a question of fully connected versus group connected versus adding the non-diagonal aspect in there. So we produced some results where we have we had the non-diagonal connect. So now the connections, we made the connections in this dimension here. So what you can see is that the group connected and both the non-diagonal and the sort of conventional group connected have higher achievable rate compared to just the flat RIS. And then the non-diagonal has also some advantage on the group connected architecture. Okay. And then here we're comparing it with the star RIS, where you can think of it as just two sector RIS, and the performance again is with the group connected is better than the RIS. So again, as I said, this is just quick overview, motivation of the work, and then there's still lots of open problems and questions to answer in there. So just a quick summary based on the different webinars in this series and what I covered today. Beyond diagonal RIS offers flexibility in the design, but then we need to look at it as a trade-off. Performance, computational complexity, implementation complexity, and cost. Clearly, we need to consider more in terms of how to best implement these architectures. The results I showed today were mostly assuming idealistic scenario where we have ideal hardware and basically ideal channel knowledge at basically everywhere in the network. And then the question is, how does this perform when you start considering realistic hardware impairments and realistic channel estimation? Do we still see this gain, or do we lose in terms of this gain? Then another question is, this beyond diagonal RIS, can we use it in the passive versus active? Can it be used in holographic MIMO? Can it be used in stacked intelligent surfaces as well? So basically, how do we do the connections there? And then there's lots of work as well on the use of RIS and integrated sensing and communications. So what advantage would the beyond diagonal add to this? Well, thanks for your time. And now, any questions?
All right. Yeah. Thank you so much, Mohammed, for the excellent presentation. So I can see there are no comments from the chat, so we can go directly to our attendees here. So please use the raise hand tool provided by Zoom, and then we'll try to take some questions. All right, since I don't see any hands raised yet, maybe I can get us started. So Mohammed, I was wondering if you have any thoughts. I know you mentioned that more implementation and practical considerations are required, but do you have any thoughts around the practical feasibility of having these approaches to designing RIS, so the beyond diagonal approach?
Yeah, I mean, this question is always raised, and this actually was the first thing we thought about when we were proposing this, or we were thinking about it, because then the question is, okay, so mathematically it does work. How would this work? I'm not an expert in this area, so I went and talked to some colleagues working in the implementation of this, and they did propose some architectures where we have some switches with some impedance networks. They also proposed to use some, I think they called couplers and isolators. And then the question would be, how would you sort of route the signals between these? But I mean, based on my discussions with colleagues, it is feasible, the implementation.
Okay. Yeah, thank you very much. Okay, we can see one hand raised. Go ahead, please, Askin.
Hi, thank you for presentation. I'm wondering what is the effect of mutual coupling between RIS elements? Like, does it have huge impact on the reflection matrix, like diagonal case?
Yeah, I mean, there is work on this. We haven't done it in the non-diagonal case, but it will definitely has its effect on the performance. But then I think the question is, what's this effect? How much is the loss compared to the conventional one? Which I don't have an answer now, but we're working on that. But yes, I mean, the expectation is it will have an impact.
So may I ask a follow-up question? So for example, conventional one, if we assume like single connected case, does it also, if we also consider the mutual coupling effect, does it also create a non-diagonal matrix? Because when we send a signal to a signal element, and then that may impact on the other elements also. So this is also a non-diagonal matrix problem.
Yes. So if we think about it from the non-diagonal perspective, so if we look at it as non-diagonal, then the question is we're trying to sort of optimize the connections and then optimize the phase shift angle. Then what you're saying is it will make it non-diagonal, but then the sort of the non-diagonal elements are annoyance rather than something you want to optimize. But it's something you have to consider there. And then the question is, how would you optimize the problem so that you take that into effect? And then what you can do is you can sort of match the or model the mutual coupling statistically, and then see how that affects your performance. Does that answer your question?
Thank you. Yeah, thank you.
Okay, so next we go to Hamad. Go ahead, please.
Thank you, Prof. Mohammed, for this great talk. So my question is about the principle of non-diagonal RIS. So it relies on designing the permutation matrix at the RIS, right? So let's assume the following scenario. If we have the channel already ordered, the forward and the backward channels are ordered already.
Yeah.
Can we have such scenario? And in this scenario, do we have any gain of the non-diagonal RIS?
I'm not sure I understand. So when you say it's ordered already, what do you mean by that?
So the channel gains, if we consider the SISO case, we have a base station and the user. If the channels, the forward channel is already ordered based on the backward channel.
No, but you don't have control on the channel, do you? So we don't have control on the channel.
I mean, do we have such scenario in practical sense?
I mean, given we don't have control on the channel, I would say probabilistically it is possible, but the probability is very small. Because again, the channels, we don't have control on them between the base station and RIS user equipment.
Sure, thanks.
Okay, thank you. And next, go to Zina.
Hello, thank you for the presentation. My question is about the multi-sector RIS. Which criterion is used to do the allocation of such number of element to, for example, the base station and the other for the user? Is it the maximum SNR or another criterion? Thank you.
Yeah, so as I mentioned in the talk, so there are lots of open problems in this here. So in our simulation, what we did is we just assigned the numbers just randomly. We didn't do any optimization in terms of how we would assign the number of elements in the sector. We just did simulation for 6 sectors, and I can't remember. Let me try to find if I have the number of elements per sector. I think it's around, well, oh yeah, so we varied the number between 6 and 60. But yeah, we didn't optimize the numbers there, but it is something which can be considered in the objective function.
Okay, I think so. It's a random allocation of the numbers.
In our simulation,
not
yeah,
based.
we didn't take that into consideration.
Okay, thank you so much.
All right. Any other questions? We have time for one more. Yes, go ahead, please, Matthew.
Hi, yes, thank you. Thank you, Professor Mohammed, for the nice presentation. I had a question regarding channel estimation, if you have some insights or it's just, it will be an interesting future research direction, because in conventional RIS, the cascaded channel is often estimated and is sufficient to optimize the reflection coefficient, but with a non-diagonal architecture, do you have an insight in this regard?
Yeah, we haven't got results with that yet, so I can't tell you exactly. But what we're trying to do is we're trying to do as we do with the conventional RIS, and then try to see how that affects the performance, basically. And that's why I mentioned it as again a future direction for the work. Yeah.
Thank you.
Okay, so I don't see any other hand raised. I would like to thank Professor El-Hajjar for the fantastic presentation, and Professor Bruno Clares and Matthew for the nice organization, and all of you for attending and for your nice questions. So with this, we can close this talk. Thank you very much, and have a good rest of the day.